All right, well, welcome to the lecture today. As we were finishing last time, we were talking about some modern theories of electron transfer, and that included the Marcus theory, which is the most famous example and one of the most widely quoted and used theories of electron transfer. So let's see if we can finish up the ideas that we had at the end of the last time today and give you a flavor for it. We really can't do it justice in this class. Obviously, it's a very complicated subject and requires some careful study. But we'll give you some idea what's going on when we talk about Marcus theory. As we talked about before, we're talking about generally non-adiabatic electron transfers. And that's the general idea for most of these theories. And that generally means that there is little electronic coupling between electronic states between the, say, the electrode and the molecule that receives an electron or gives up the electron, or between two molecules in solution undergoing an electron transfer. And that non-adiabatic electron transfer is what makes the theory tractable, actually. If we have to include adiabaticity in the system, we have to consider things about coupling of bonds, coupling of orbitals, and that makes it much more complicated. As we said before, the basic theory has an activation factor, or a pre-exponential factor, which we will indicate as being equal to K electronic transmission coefficient, which is our electronic term. Nuclear frequency factor, and a complex equilibrium, a pre-equilibrium complex. In other words, these two, either the electrode and the molecule have to get together, or two molecules have to get together to form an equilibrium. Okay. So Marcus was concerned about the work involved in the changes with the changes in internal bond length, and angles. In other words, when we have an electron transfer, we have to go from the reactant to product, and so that often requires changing the bond lengths and bond angles, and there's some work involved with that. You can think of these bonds as being little springs or torsion bars. We have to rotate them and stretch them or compress them, and that requires work. The other thing that happens is that there is a solvation change. Almost every time we do an electron transfer, we get a change in the charge on that molecule or ion. So it goes from, say, a neutral to a positively charged ion. The solvation shell of ions around that molecule changes. The water molecules or the solvent molecules will change their orientation depending on whether they're dipoles or not. So there's some work involved in changing that solvation layer around the molecule. And he basically said that, to make it simple, he said that the activation energy, the delta G double dagger, is approximately equal to a term which he called lambda plus the delta G0 over 4 lambda, where lambda he called the reorganization energy. Reorganization. And he basically broke it into two parts, where lambda would be equal to an inner bond, lambda inner reorganization or internal reorganization energy plus an external reorganization or outer. So this would be the bond lengths and angles. And that would be the energy required for that, and this would be the solvation change energy. And delta G would be the driving force for the reaction. Minus delta G basically would be the driving force for that particular reaction. And the other thing is Well, you can read what he says about it by looking up in one of his papers. He's wrote lots of papers. One that is a reasonably good description of it is Marcus and Sumi in the J, Electron Analytical Chemistry. Volume 204, 59, or page 204, 59, volume 59. Oh, I'm sorry. Let's see. Volume 204, page 59, 1986. Okay. Also in that, remember the Marcus theory basically considered the reactant and product to be two parabolic wells. And if you take a look at that, you'll see that as we change the driving force, which basically is changing the potential for the reaction, alpha will no longer be a linear function of potential. And he said that alpha is going to be equal to 1/2 times 1 plus a term which is the driving force over the reorganization energies. So here you see where alpha is typically 1/2, and as long as lambda is large, alpha should stay approximately 0.5. But as soon as a lambda gets small, then we start to see significant changes in the value of alpha as a driving force change. Now for electrochemical process, that driving force is still the potential that we've applied. For solvent, for reactions in the solvent, that would be the basically redox potential would be the driving force for that particular process. Let's see where we're at here. Okay, let's take a look at some of our rules for electron transfer. There's two basic types of electron transfer that people always consider. One is called, often we'll abbreviate OS, or stands for outer sphere. And outer sphere is our non-adiabatic type transfers. And basically, O and R species don't interact strongly with each other or with the solvents, so strongly with each other or solvents, and usually have little internal rearrangements. An example of an outer sphere electron transfer might be, say, the reduction of anthracene, which is this polyaromatic hydrocarbon. If you reduce anthracene, it's a reversible process, and you form a species that's the radical anion. Oops. Sorry about that. But because of the size of that material, there's little internal rearrangement. The benzene ring structure stays basically the same. There's hardly any change in the structure. There's no bending. There's no twisting at that point, very little of that. And there's also very little solvent reorganization because that molecule is pretty large for molecules. It really doesn't, the charge that's put onto it is not very significant. There's very little charge density. So that would be a good example of a outer sphere electron transfer. Now Marcus said for outer sphere processes, there is a simple relationship between the electron transfer rate that we can measure electrochemically, which is K0, and he says K0 divided by this Z electronic is equal to the square root of a rate constant he called K sub EX over Z solution. Now KEX is the self-exchange kinetics, or the electron self-exchange kinetics. And it would be basically taking a molecule like A plus A minus going to A minus plus A. So the reaction for that. Now that kind of reaction is a zero driving force reaction. There's no delta G difference. The redox potentials for A and A minus, because they're a redox couple, is zero. There's no difference between those points. So there's zero driving force. So the only driving force for that or the only reason it occurs is that it can occur, and that the rearrangement process is what's governing that particular process. And you can measure this by using radio-labeled compounds and things like that. And Z electronic are what they call collision frequencies. And for solution collision frequencies, we're talking about a number they typically quote 10 to the 11th per mole per second. In other words, they're talking about molecules banging together, how often they're doing that. It's related to the concentration, obviously. And the Z electronic is another collision frequency, but in this case it would be the rate at which the molecule ion bangs into the electrode with time, and that's going to be a term that's like the mass transfer terms that we've seen before, about 10 to the 4th centimeters per second. And people have made graphs of this relationship and these relationships. They've measured those two, and you see there's a pretty good agreement between the solution phase electron transfer process, the exchange rate, and the electrochemical process. What is especially apparent is that they see this effect for slow rates of electron transfer. As they go to faster rates of electron transfer at electrodes, this relationship starts to break down, and that's not clear yet why that is. Some people think it's an experimental artifact, and some people think there's some problems with the theory at higher driving force processes that Marcus has not taken into account. So there's been all kinds of theories that have been proposed, modifications of basic theory to account for that. Also, if you go back and look at our notes, you'll see I mentioned that alpha can change, and in fact, this has been observed experimentally in a number of cases. What often people see as a change in alpha, though, is an artifact. They see, because they haven't carefully taken into account the fact that just because they're changing the external potential, the driving force is not necessarily linearly related to the potential that they've applied. What can happen is there can be a potential, an extra potential that develops at the electrode solution interface. We'll talk about that a little later. And so sometimes you'll see changes in alpha that are apparent, but they are actually not the same changes in alpha that you see here, particularly for highly charged species. However, there has been pretty good understanding that a few reports of potential-dependent alphas have been reported and that are credible in the literature. One of the things that Marcus did was predict this in the 1960s, and it took a long time for that to be observed, but in fact it was, and that's one of the reasons he got the Nobel Prize, is because of all these predictions he could make, and with this theory, and that were later shown to be true. Another prediction Marcus could make that you might hear about, I'm going to just briefly mention. It's not necessarily an electrochemical process, but it's something that sort of goes along with electron transfer. That's called the Marcus inverted region. And what happens in the Marcus inverted region is that, unlike your intuition, typically we would think, well, I have a reaction between two molecules, and we're going to try to make that reaction go faster. How can we do that? Well, we've already seen in electrochemistry we can turn the potential up, and that will make the reaction go faster because the delta G has been increased. We've increased the free energy of the reaction. And typically that reaction rate will increase until we hit to some sort of a mass transfer limit. The diffusion rate cannot keep up with the rate of electron transfer. But in fact, if we kept the mass transfer rate was basically infinite, what we would see, according to Marcus, is what he called an inverted region, which is anti-intuitive, that as we increase the driving force of the reaction rate would increase to a point, and then it would start to decrease. And that decrease in rate with increased driving force is what they call the inverted region. And this has been observed for solution phase species. Again, this was something that was predicted in the 60s and was not observed until later. The basic idea, again, is you remember the potential wells for the reactant and the product of the system. And we can think of, again, the driving force for the reaction, delta G, 0. And as we increase the driving force, what can happen is that these potential wells slide past each other, and the second potential well can actually slide to a point where it's, say, here. And so all we've done is basically dropped that well down, but now notice what's happened is that the intersection now has got to a minimum here, and now it's going to go up. And if we kept that process up, you can think about the second well completely enclosing the first well. And that's where we see this inverted region. The rate will now decrease because we require an additional amount of energy to get that reaction to go. And actually this is seen in most prominently in biochemical processes that are highly favored, such as electron transfer, photoelectron transfer. Photosynthesis is a good example. We put in a energy in the form of a photon. It's got a large amount of energy, so there's a large amount of reaction going in. You'd expect that because there's so much energy in that system, it would immediately fall back to the products. But in fact, because that is now in the inverted region, the back reaction is quite slow. And so even though highly excited species can be stable because they, in order to react, they would be reacting via an inverted region process. And so things that would normally decompose in a few femtoseconds, you'd think, can last for microseconds or milliseconds on a time scale. And that's one of the reasons photosynthesis works. It can go up a ladder of energies by prohibiting the back reaction by operating them in the inverted region. Okay.